Yeah. All right, so I'm gonna continue from where we left off yesterday. So what we had, so we so we had this amplitude for n+1 particles, where the one was the special one referring to a soft photon. By the way, the other n particles could be any, it could also be photons. Okay? But I'm just focusing on the one that has energy going to zero. So by soft photon, what we meant is that, so omega, so this is the photon energy going to zero. So in that limit, what we obtained was, we obtained that the amplitude get factorized into a soft factor. And then we had things of order 1. So it was important to mention that this thing was of order omega to the -1. So this is the first time that one sees an infrared divergence right away, even at tree level. And what we obtained was that this sub-factor was given by this expression over here, epsilon mu, q mu, no, what was it? pi mu divided by pi divided into q. And importantly, it was here, this was the electric charge. So this could be, plus or minus the charge of the electron. So it's just two possible numbers. But of course, since this photon could be, when we did the computation, this was coupling to some external electron or positron, then to the positron it couples with with the sign of the charge, and to the electron the charge is with the opposite sign. So that's why we give it there. So what we wanted to do, what we said that we were going to do today, was to test gauge invariance. And I know that, so since this is a school, I have to say things more school-like. Something like that. So gauge invariance means that, for example, if I looked at the photon field, the A mu, then this is what happens in space-time. But if you go to momentum space, this translates into a shift. Let me call this alpha, just any function. Let me call it this. So it corresponds to a shift in the polarization vector, which under a gauge transformation transforms like that. By the way, you could have instead of checking gauge invariance, you could have said the same thing if you wanted to check Lorentz invariance. That's a little bit more natural to us in the sense of scattering amplitude. We want the scattering amplitude to be a Lorentz invariant quantity, and in that case, this vector, if you wanted to do it that way, you can also do it. This transforms like something like that. Plus also it has some homogeneous part. Okay? So this is a prime. Okay? So this is under Lorentz. Okay? So you could play the same game that I'm going to play with gauge invariance. You could do it with Lorentz invariance, And in that case, you will be checking Lorentz invariance of the action. I'm going to check the H invariance of the action, but I chose this one because it's basically the same, and I don't want to be carrying this gamma, you know, all the way. So it's basically the same thing. By the way, from here, you can see right away that the polarization is not a 4-vector. You see, even though it has a Lorentz index, it's not really a 4-vector because it does not transform as a 4-vector. It has this inhomogeneous part, which is spoiled. The usual thing that we learned at the very beginning, that how Lorentz vectors transform. Okay, so let's check this. So under gauge invariance, the amplitude, of course, has to be invariant. Okay, and I'm ready to pick. So let me do it here. So I'm going to write this in the following way. So I'm going to rewrite this, that equation over there. I'm going to write it in the soft factorization form already. So if you bear with me, if you can see this, this will go like this, that, like that. So I'm already doing this, okay? So the amplitude will go this. So this is the same as before because I just replaced mu with this mu, but plus, we have plus this I can pull it outside because it does not depend on anything else. EI, PI mu dotted into Q mu divided by PI dotted into PQ. Okay, sorry about that. And this has to be equal to the same thing as before. Okay, so this is precisely this, right? The full thing. So this better be 0. Okay. That is the usual thing of, and sometimes that the shortcut is like when you see the books, you just say the amplitude when you replace the polarization by the momentum of some of the particles of the process, some of the gauge particles of the process, that thing has to vanish. Okay, that's all I'm saying here. Sometimes it goes under the fancy name of water identities, but it's nothing more than this. Okay, so can I? Doesn't offer. Yes. So again, maybe. So you see right away that this is EI dot Q that goes all the way to that one over there. Right, so that's the important thing. So, so as a consequence, we have that has to be equal to 0. So this is saying that the sum of all the electric charges that go into the scattering process has to add up to 0. So all of the charges that come in has to be equal to all the charges that come out. So this is charge conservation, right? Okay. Okay. So that's a nice check that these things provide. Okay. Yeah. Oops, sorry. Okay. Now. So we did that example for that was for a scalar QED, but remember that we also said that the same subfactor is also the same for just the good QED, the correct theory of electromagnetic interactions. And also it's universal in the sense, so the subfactor, so the subfactor is 0 is universal in the sense that it takes the same form in any theory with photons. Let me just say something fancy about it. So all the particles are, when we say particles, these are excitations that are in the Fock space of the theory. So we call that the spectrum of the theory. So you have any theory that you want where there's a gauge field, there's an immediate gauge field, then that subfactor is always the same. So the amplitude always factorizes in that sense, in that way, and that's why it's called universal. Moreover, okay, no, I'm not going to say more about this. Yeah. Now, this is a school about quantum gravity. So what about gravity? The same thing, and now I have a soft graviton instead. Okay, so a soft graviton, I'm going to call it at for momentum q again, but now its polarization vector is going to have two indices, two Lorentz indices, because it has spin, right? And just as a reminder, remember that that has to be, for the graviton, it has to be symmetric and also traceless. That is the graviton, right? The antisymmetric part is called the Karl-Ramon field, or B field, in other words. And for example, the trace is also a field, and that is called the dilaton. Okay? So I'm going to focus on the graviton in this case. All right? So what if we play the same game? And this was Weinberg, 1964. We get that the amplitude again in the limit when the graviton now goes soft, again factorizes in a way as before. We get again, let me emphasize that we get again the same structure. I put 1 yesterday, but let me put omega to the 0 just to be a little bit more precise. Let me go back a little bit here. Let me just point out something else. I think Matti was asking this yesterday. That is another point. If you continue, for example, here, this is just the first term in this Taylor series and this power series. You can compute more terms. In general, you get some sort of factorization like this, okay? Where this is of order omega to the -1, this is of order 1, This is order omega, and so on and so forth. And I think I mentioned this yesterday. So this is 3-level exact. In the sense that if you compute all loop corrections, all possible loop corrections, they're all 0. So the 3-level result that I computed is the exact subfactor for the entire all loop amplitude. Okay. This one here, surprisingly, is 1 loop level exact, in the sense that here you have 2 terms. You have 1 term coming from 3-level, 1 term coming from 1 loop, and then from 2 loops and on, they're all 0. So in that sense, it's 1 level, 1 loop. I mean, 1 loop, 1 loop exact. And guess what? This is 2 loop exact. Okay. And you can ask, of course, if that pattern continues. I think it's right, but I don't remember quite well the literature. So if somebody's interested in that, I can send you some literature about it. Okay. But yeah, okay, that's it. This was an abelian theory. For non-abelian gauge theories, this is even up to here. This is pretty much like uncharted territory. Okay. It's something that people are working on ferociously still, and things are not settled by any means yet. Okay, so if we play the same game now for gravity, now when you want to, I'm not going to write the equations. I'm just going to say it. Because also I think that many of you already know these things. So how would you go ahead and compute a graviton amplitude using Feynman diagrams and things like that? So it's pretty much the same thing that you're used to. You get the Einstein-Hilbert. You start with the don't write this if you don't need to write this. So you start from the Einstein-Hilbert Lagrangian, and you bastardize it by expanding the metric around flat space. You put that all into here, you put it into the determinant of the metric, you put it into the Ricci scalar, you expand, you get a horrendous thing. But at the end of the day, you're going to end up with an action in flat space for some complicated interactions of the H field. And this is the field called the graviton. And then you start computing amplitudes based on that action. Okay? So that is the premise of all these computations. Okay, so if you did that, you get again the same thing. And a 0 for the case of gravity. Okay, you get. Let me. Okay. Similarly to Francis Lowe, when I mentioned that he did it for QED in 1958, Weiner in 1964 showed that the same thing happens. That in the sense that the leading order, so the leading subfactor, the S0, also comes from the coupling of the graviton, of the subgraviton, to one of the external states. Now this is state. Now this, remember that gravity couples to everything, right? Everything gravitates, right? As long as you have energy, particles attract through gravitational interaction. So this graviton here couples to any of this, could be an electron, a positron, a neutrino, or whatever, any particle, right? So there's always some interaction strength here. Let me just, for the sake of dramatic reasons, let me just call it GI, okay? And we're just going to assume that, for now, for a few minutes, we're going to assume that the graviton couples to this particle with some strength. If it couples to another particle, it couples with a different strength, and so on and so forth, okay? And So Weiner showed that a leading order in the soft expansion, these are the diagrams that dominate, and in this case the soft factor is very, very similar to the other one, but now we have, instead of the electric charge, we have this coupling constant, GI. We have the polarization tensor for the tensor for the graviton, and then now here it couples to. So it's contracted with two copies of that external momenta, and then in the denominator, because the propagator in gravity pretty much has the same form of the propagators in QED or in any theory, basically. This is what the soft factor looks like for the case of gravity. Okay, so before it was just one index and one thing here. So for spin 2, you have that over here. Okay, and now we ask the same question: what about gauge invariance, right? So gauge invariance at the level of graviton amplitudes. What does it mean at the level of reaction?
Invariant on the change of coordinates.
Invariance under?
Change of coordinates.
Yeah, exactly. The general coordinate transformation. So diffeomorphisms. So the theory, of course, has to be invariant under diffeomorphisms. The Lagrangian, of course, the action, of course, it is. And so now we play the same game. We do a gauge transformation. And for spin 2, you can check that you get something very similar. This could be any function of the momentum, and now it has. But this has to be, since this guy is symmetric, this also has to be symmetrized. Okay, so that is a gauge transformation for a spin 2 particle. Massless spin 2 particle for the gravity, because this is the symmetric part. Okay, so if you do that, then notice that what we get now. So the amplitude has to be invariant again. So what do we get? We get the same thing as before. Yeah, I'm not going to write it. Right? This thing is going to give this contribution over here, right? This is what we know from the self-factorization. So under this, we're going to repeat that, and then we're going to get. If you help me out here. Di, I'm going to get this outside, and then we're going to get Q mu Pi mu Pi nu. Am I doing it right? Yes. And because, plus the other one. Well, there's you see, it's going to be, because of the symmetrization, we're going to have a 1/2, and this is going to be exactly the same value as before. Sorry, I forgot the Pi dot Q. So Gi Q Q nu again. Pi. What is it? Nu. Yeah, did I do it correctly?
Do you have 1/2?
What?
1/2?
Because the anti-symmetrization, it's 1/2.
But
It's divided by half.
the product factor of momenta is symmetric.
Huh?
You don't need to do that.
Yeah. This becomes, you change indices, and this becomes the same thing here, and then we get that. Then we get just one of these. Then Gi, and then Q dotted into P again, and we get Pi mu. Yeah. Okay. So and so now this guy has to be equal to 0. So you see, like, this one goes away here, and what you get is that the sum of all is equal to 0, right? But there's one more thing that this is also, of course, true for the previous example. We also know that because of translational invariance, the sum of all the momenta has to be equal to 0, right? Observational momentum, right? So you have to satisfy these two constraints. This constraint and this constraint, right? Now, but the crucial point is this. This has to be true for any external momenta of the particles that you're scattering, right? Yes? So I have the amplitude, I can choose my external particle, I can prepare my external states in any way I like, and then I compute the scattering amplitude of this process. So all the directions of the external momenta is at my, they're at our disposition. So I have to satisfy this, okay? And I also have to satisfy this, okay? So you can clearly, you can rapidly see, if you play around a little bit with this, is that there's no way you can satisfy this and satisfy this for arbitrary momenta, There's no way you can, if this is there. So your only solution is that thing is a constant. You see that? You see why? Yeah. So so this coupling here has to be a constant, such that you can take it out, and then this constraint is just the same as that constraint. So what we're saying is that the graviton couples to every other single particle with the same strength. That is called equivalence principle. Equivalence principle. Yeah. Okay. So, and actually, to be more precise, that G actually has, in order for these amplitudes at low energies match with Newton's, 1 over r, or 1 over r squared, for the case of the force, has to be the square root of 2 pi G Newton.
Yeah. So we force that momentum conservation, or we just got it from somewhere?
No, it's imposed up to you. I mean, it's imposed onto you by by Poincaré invariance.
Oh, okay.
Right? Your amplitude from the very beginning, you stated that you're doing special relativity, right? So, okay. All right. Okay. So I mean it's pretty remarkable that that this simple computation by Weinberg, gives you the equivalence principle that all particles have to couple with the same strength to the gravity. I mean through gravitational forces. Okay. Let me do it here. So you see a pattern already at the for the soft factor. Right? For spin 1, it was just 1 momenta. For spin 2, it's 2 momenta. What about spin 3, 4, and 2? Could we play the same game? Spin 3 or higher. Okay. So Fronsdal in the 1960s, I forgot the exact year, but in the 60s he developed a theory of three higher spin particles, and what are the Maxwell's equations for spin 3, spin 4, and for massless higher spin particles in flat space, and that is completely consistent. Okay? There's no problem about that. But what if we do this? So in that case, And this is also, what I'm going to show is also in Weinberg's paper from 1964. It's the same thing again, okay? Now the subfactor has this form. Now you have a spin 3 polarization vector, and you get 3 of these momenta divided by pi that q. And now we do a gauge transformation. And if you just read Franz's paper, it is what you expected. It's like that. And then you get some function mu of the soft momentum, like that. And you have to completely symmetrize the 3 indices. If you play the same game, then you arrive at the following conclusion using gauge invariance and okay. And I guess you guys already know where we're going to. Okay. So we do that, and now we have to impose that you get pi, and then pi gets the same thing happens, so that has to be equal to 0. So now this, by the way, now let me call it G Tudo for the coupling of this spin 3 particle, this massless spin 3 particle to everything else, and I get you get that constraint, and don't forget the constraint that we have from the very beginning, that because of the space-time translations, the total momentum conservation is obeyed. So now I have to satisfy this and this. And here there's no way you can solve this unless you set this thing equal to 0. That is the only solution, right? So this is telling you that spin 3 particles, massless spin 3 particles, cannot couple to matter, at least in the low energy limit. I've been saying soft theorem, so we are in the regime of so at high energies, weird things can happen. But in Weinberg's paper, it's in the I forgot if it's in the abstract or in the conclusions, that the phrase is pretty nice because it says, therefore we conclude that the only long-range interactions that can exist in nature are the ones mediated by photons and gravitons, and that's it. So you can only have Coulomb's law and Newton's law, 1 over r, and that's it. Okay, there's no more. All right. Okay, so I think that's pretty much what I wanted to say about soft theorems. Oh, yeah, 4, 5, it gets even after. Okay.
Rachel, have you got 2 soft photons?
Sorry, what?
If you have 2 soft photons, you can say something?
Yeah. I did not want to go into this thing. In that paper, it's also in Weinberg's book. So, why not 3, 4, 5, things like that, right? So you have these are called multi-soft theorems. Yeah. And in Weinberg's QFT book, I think it's in the chapter which is called infrared divergences. He shows the computation in QED and also in gravity. So I'm only doing, one part of the full amplitude of the thing that you would observe in the detector at the end of the day, or one of the things that should be going on in reality. Is that okay? I have 1 photon coupled to this, but I can have 2 or 3, and so on, right? And then I have to sum, the same sum over the external state. So you have to add up. You have to add up the amplitude with 1 photon, with 2 or 3, all up to infinity. right? So the nice thing in this computation is that because this is a boson, then you have to include the symmetrization factor of just boson in the statistics, right? So that comes with 1/n. You sum this all up, and you get some power of n, because you have these powers of omega, like that. And this precise the exponentiates to exponentiates. So the full amplitude with all possible multi-photons coupled to the external legs, you can resum that thing, and you get an exponential, and it's usually written like this. So the amplitude, the full amplitude, it has some soft, something like that, to something here. That's what's called the hard factorization. So yeah, but I don't want to get too many.
Could you repeat the conclusion, the final conclusion for the spin 3?
For spin 3?
Yes.
That the only way, I'm not sure if this is what you mean, but let me just say it.
Yes.
So,
Is I just want to hear it again.
okay,
The
so.
conclusion is too strong.
Yeah, it's pretty strong. Yeah. I agree. It's pretty strong. So, in order to satisfy these two constraints, for arbitrary momenta pi, then the only solution is that this is equal to 0.
Okay.
Right? So okay, that was not what you looked for.
So you're saying there cannot be any spin 3.
Yeah.
But,
I mean, I didn't say
there
it.
are
My
some
mistake.
hidden assumptions.
Ah?
Sorry?
Yeah, I understand. Yeah, the theorems are as strong as their axioms. I agree.
Exactly.
So
there
yeah,
are
so
hidden
what?
assumptions.
So the assumptions are: you have a theory that has a finite spectrum. So in the case of gravity, it's just whatever tensor you couple to GR. In the case of QED, for example, it's only like 3 particles in the spectrum: positron, electron, and photon. That's it. Even in QCD, you also have a finite spectrum: quarks, gluons, and that's it. Right? So. So in Vasilyev's higher spin theory, you have an infinite spectrum. So in that case, that evades.
Size is ADS.
And yeah, that's the other assumption. I'm doing Minkowski. So in Minkowski,
You probably are assuming local, that the theory generating these amplitudes, it should be local.
yeah. I mean that in QFT we always start from local QFT, right?
Infinite derivatives.
Yeah, okay. Yeah, but what about string theory? You see, in string theory,
There are infinite number of particles.
exactly, you have an infinite tower of higher spins, but it's infinite. So it's in flat space, but it's an infinite tower. So that also string theory also evades this theory.
Okay, so spin 4 in string theory is also massive. So this
Say that
is
again?
massless. This is massless, right? This is massless spin 3.
Yes.
In string theory, it's massive. So it already
Oh yes.
out of the
Yeah, I was thinking about Vasilyev's, which is the
Oh,
tensionless
okay.
limit, and then all the massive states collapse into massless.
Yes.
Yeah, no, but yeah, you're right. Okay. Sorry.
So, that's it. This doesn't work for Cameron.
For what?
Cameron doesn't work.
I think I haven't studied it in detail, but I think you can do it for Calvert as well.
You have symmetric factor times an anti-symmetric factor.
It can't be only spin 1. So that's spin.
So you're saying because in Calvert, for example, you would have like just the symmetric part, and then you're saying that the thing maybe it's
With that in the next zero, the factors of momentum, yes, is always symmetric on the indices.
So you're saying that because if you have the anti-symmetry, the thing goes to 0, and you get 0 equals 0 and no further information?
S0 is 0.
What?
Is S0 is 0.
Maybe I have it. But yeah, I'm under the impression that if you did that in that case, then you get some kind of triviality, like 0 equals 0. And everything works out, but yeah, that doesn't give you any information. Okay, maybe a few more things that I can say before moving on is, as Matthias was asking yesterday, what is the form of that S1 and what is the form of S2? So in the case of gravity, also in the case of QED, that S1 has the Lorentz generators in it. So that factorization is kind of a differential operator acting on the amplitude. And then if you play the same game with doing gauge invariance, I'm talking about the case of gravity or the case of QED. If you do the same thing, then at what do you arrive at? So for example, if you do it in the case of gravity, at leading order, the S1, you arrive at momentum conservation. Okay? No, I'm sorry. At leading order, you arrive at momentum conservation. At sub-leading order, you arrive at angular momentum conservation. Because you have these differential operators, which are the momenta. It's actually the angular momenta operators. Okay, the genuine, but basically that has, has the usual Lorentz generators and the spin generator. Okay, and yeah. So for example, in the case of QED, you get at leading order, you get charge conservation, then you get momentum conservation, and then you get angular momentum conservation. And then you may ask, okay, if you keep going on, then will you find more conservation loss? And the answer is that no. You get trivial state, you get 0 equals 0, 0 equals 0 everywhere in the entire series. And of course it had to be that way because you have no longer more charges and you have no more conserved charges in the theory. You only have Poincare, and that's it. And charge conservation, which is the global unit. Okay. So everything works out pretty neatly. Okay. So according to my plan yesterday, now I was going to go in the opposite extreme. So we're doing infrared physics, soft theorems, and now I'm going to go in the opposite extreme, high energy scattering. So ultra Planck scattering. And in my third lecture tomorrow, through this program of celestial holography, I'm going to show you one way, there are more ways in which the UV and the IR are connected in some very interesting way. Okay, so that usually goes under the name of UV-IR connection. And for example, ADS-CFT is an example, by what's the word? ¿Cómo se dice? Vaya, por excelencia, un ejemplo por excelencia, ¿cómo se dice? But in English, I forgot the word, but okay, you know what I mean. So in ADCFT, you get that, for example, UV physics at the in the boundary corresponds to infrared physics in the bulk. So that's pretty remarkable, and that is not the only place in which you see these UV-IR connections. For example, one that is also pretty nice, and it's actually from the very early days of the string theory. It's what's called the open-closed string duality. Just because we brought this into the table, let me just. Okay, no, I'm not going to say it. I might say it later on. Let me just continue. So. Quantum gravity at extreme high energies. So, okay, so the strings at high energies. Let me just. I'm going to say just very rough things about string amplitudes. In order to arrive at the string amplitudes, usually one does like a full semester course in the string theory, and even then, at the very end, what gets at the point in which you can start writing an amplitude. So let me just give you. I'm talking to the students in the audience, of course, they're experts here on the string amplitudes. And so, in a string theory, what basically compute is something like this. Let me focus again on a 4-point amplitude, because it's the first amplitude which is non-trivial, just in QFT. I mean, kinematically, it has more structure than just a simple 3-point amplitude. A 3-point amplitude basically has no kinematic dependence. So most of the times it's just the complement constant and momenta, yeah, it's not. So at 4-point you see more structure. So and that's what we will do also in the case of the string. And if you wanted to compute that, so look what we're doing here. We're taking, so this is an open string, okay? So this is the final, this is, for example, time, if you will, this is space, okay? We have this worksheet, right, which is stripped by the string. And then, for example, what happened here, these are free strings. In order for them to be free strings, you have to imagine them to be very, very far away and very well separated from each other. You have to be able to define free asymptotic states. This was a given, actually, from the very beginning yesterday when we talked about the S matrix. The S matrix, you need to define states that are very well separated from each other such that they be considered free. And by the way, that is only possible up until now in flat space. For example, in the sitter or in anti-de Sitter, that's not really possible there, okay? Because it's basically because we have a scale and in the strict sense, there's no S matrix. There's no way you can when the cosmological constant is not zero, either positive or negative. There's no really the definition of an S matrix because you cannot really define asymptotically free states. Okay, so flat space is very special in that sense. So these strings should be, far away, defined very far away, such that they're no longer interacting among each other. But then when they get close, okay, they join there. So that is what that diagram represents. And now you have just one string, okay, and then here they separate again, and you have two strings in again. This is no surprise. In quantum field theory, you do this all the time, right? When you have a diagram like that, you have two particles, they join there, they annihilate, they form a new particle, and then this particle, splits up again into two particles. It's the same thing. And also, even though the strings have they're extended objects, in some sense, they behave like non-local interactions. The interactions are really local, in the sense that when you study the scattering amplitudes of these objects, and you use all the machinery that has nothing to do with QFT or string solidity, just has to do with very primitive concepts like unitarity, which is a given in quantum mechanics. Probability has to sum up to 1. Lorentz invariant, all those things. You realize that even these extended objects, which are the strings, behave locally as a mathematical object. Okay? They correspond to local interactions, and that is basically because when they join at one particular point in the spacetime. So the interaction which occurs there is actually local, even though the full thing does not look local. Okay, so that's one thing. So imagine that this is it's impossible to do this computation. If I have just a string with some shape in a space-time, another one, I make them join, and then I let some time pass, and then I open it up again, and I compute. That object would be impossible to compute. if we're not for conformal invariance. Okay, so conformal invariance it's crucial because the theory that governs this interaction is a two-dimensional theory, which is the theory on the worksheet. So if you heard, the body of action or the dynamical of action, you have a two-dimensional action for a minimal area surface of that string, of this configuration of the strings that sweeps that surface. But and that theory is conformal. I'm not going to get into details about conformal invariance of string theory, but that conformal invariance allows you to change this shape into the shape of a disk. So you see that this thing has a topology of a disk, but there's a little caveat. The caveat is that it's not exactly a disk. It's a disk that has some little punctures here. So here, this thing is open, right? So there's little punctures, and these punctures, what people realized in the past is that you can replace that asymptotic states with things called vertex operators. Vertex operators. That correspond to insertion or injection of momentum, injection of momentum on the worksheet. Okay? So this fact that you can change this topology to the topology of a disk, and the fact that you can replace these external states that are labeled by some external momenta, you can replace them by some operators inserted on the boundary of this disk is what allows you to compute this object over here. Okay. Okay. So this is conformal invariance. Okay. So, as you see, this, for example, in the case of a 4-point amplitude, I have the insertion of 4 vertex operators, and now notice that there are theta 1, theta 2. So there are 4 angles, and in principle, when you compute the scattering amplitude, I have to compute this object, some prescription for what this object is. But again, since we're doing quantum mechanics, this vertex could be located anywhere on the boundary of this disk. So you have to sum up all the possibilities. So that means that I have to integrate over the positions of these 4 vertex operators. Okay? That's what you would have to do in principle. But there's a leftover invariance, however. There's a remaining invariance, which in the case of open strings, which is the one I'm doing right now, is SL2R. Okay. So the SL2R group has, because it's a real, it has 4 let me just write it. So for example, I send X to, this would be SL2R. So if I have just some real variable X, if I send it to that, AD minus VC different from 0, These are called the SL2R transformations. So notice that it has four parameters in one constraint. Actually, so this has to be finite. And usually one normalizes that number to 1. It doesn't need to be 1, but usually this is what you usually do. So you have 4 real numbers in one constraint, so you have actually 3 numbers that you can choose at your own, you have at your disposal. So that means that even though in principle you have to integrate over 4 vertex operators, you can fix 3. Because of this invariance, you can fix 3 of those vertex operators to any location you want on the boundary of this disk. And at the end of the day, you end up integrating just 1 variable. Okay? So this means that this allows us to fix 3 of the 4 vertex operators. Okay? And thus the string amplitude for 4 particles looks like this. So if you remember from yesterday, the amplitude, we always write it in terms of as a function of the Mandelstam invariance, and the Mandelstam invariance for the case of four particle 2 to 2, right? There were 3 Mandelstam variables, S, T, and U, but they satisfy a constraint. If you remember, S plus T plus U was equal to the sum of the masses, the square of all the particles. So you have 3 Mandelstam invariants, but you have 1 constraint, so you have 2 Mandelstam invariants at your disposal at the end of the day. So the amplitude is only a function of 2 of them, and typically S and T are the ones chosen, and U is written in terms of S and T. Okay, so this looks like a integration over just one real variable, x, and the range of the integration. Okay, it's some range. You can do some change of variables such that it looks like this, and then you have here some function that depends on S and T, and this is what it looks like. Okay, it's a very simple thing at the end of the day. For 4 particle scattering. For n, so we're doing strings. We're doing three level strings. In that case, in principle, you have to integrate over n vertex operators, but you can always choose the 3 of them. So at the end, you end up integrating over n minus 3 real variables of some complicated function of the momenta of the particles. Okay.
So I have a question. You had said that the string joining and the string splitting only happens at a single point, and that's why at the end of the day the final result looks local. But through the conformal invariance of the worldsheet, the actual point of joining and splitting is not well defined, right? Because at the end of the day, the question of where on the perimeter of the disk the joining and the splitting happened is meaningless, no?
So, in order to give a precise answer, can you say again what goes wrong?
Right. So
you said something about
right. So the external momenta get mapped to the vertices, right? To the vertex operators, right? Okay. Right. But the points where the joining and the splitting happens, the conformal invariance doesn't keep track of where it happened, right? So, at the end of the day, it's just the shape of the word sheet.
Yes.
It's nothing more than that.
Exactly. Yeah.
Right. No, because you had said that that because the joining and the splitting happened at single points, the result looks local, and I didn't understand what that means because the conformal invariance doesn't keep track of that.
Yeah. I know. I agree with you. I totally agree with you. Now, in order to support my statement about that this thing happens locally, you will have to do a field theory of the strings splitting and joining at specific points in space. And that is what string field theory does. So if you do the same computations, for example, now I'm going to give you, for example, the computation for the 4-point amplitude in which these vertex operators correspond to the simplest string states in the bosonic theory, which are tachyons. So it's going to have this shape that, for sure, you know, the Veneziano amplitude is like an Euler beta function. And then if you did the same computation in string field theory, you get the exact same result. So the string field theory is well established in that sense. So the postulates of string field theory tell you that you can that these interactions, just like in QFT, occur locally in one space-time point. So that is what I had in mind when I said those things.
Okay.
At the level of the worksheet action with the vertex operators, I mean, I don't think I have a clear answer in my head right now. But one thing that I can say is that Mandelstam, also in the 80s or 70s, he came up with these things which are called, I mean, these are all things in geometry, which are called the Schwarz-Christoffel maps, in which this amplitude, for example, is that, instead of mapping it to a disk, he maps it to a rectangle, okay? And instead of having, you know, a point associated, like a vertex operator associated to each of the external states, he really maps it to things like that. For example, here you have one of the open strings, here you have the other open string, and here they're separated. They're separated, and in this space-time point they join. And then you have one open string, and then here it separates again into two. Okay? Now this occurs when this happens, and when this happens, it's of course completely arbitrary. So you associate some just x and y, if you want it. And then you have to integrate over all possible locations where this happens, and also all possible lengths of these things, and also all possible widths of this thing. So you have to do like an integral, it's an ugly thing. And if he does it for example, the first computation that he did in that paper, if you did it for the tachyon, you get exactly the same amplitude. Yeah, the usual one that you get from conformal invariance and vertex operators. So it's very robust in that sense.
I see. Right, and for each of these configurations, the joining and the splitting actually happened at a specific local point, but then you have to add over all of them.
Exactly.
Okay, I see.
You have to integrate over all.
Right.
Yes.
Okay.
Yeah, there was a conference in honor to Stanley Mandelstam when he became 80 years old, something like that, and the logo of the thing was something like that. Like that, some integral, and this was like this. Which is what I'm going to write right away.
Right, the Veneziano amplitude.
The Veneziano amplitude. That is the formula that gave birth to a string.
Yeah. Okay.
Okay, so in the case of the simplest string amplitude, so we're doing 4 points, tree level, and the bosonic string. Okay, this thing becomes this. Okay, so if you look at that integral over there,
Yes.
oh yeah, I forgot to say it. 4, let me be more precise, thank you as well. 4 open string tachyons. Because you can also have, in the bosonic string, you also have closed string tachyons, right? You get that over there, and this And if you look at that integral over there, it's just if you just throw it to Mathematica, it's going to tell you that this is the Euler beta function. That's the Euler beta function, and this was baptized with the name of epsilon. Okay. Okay. Let me just flash a quick result very quickly. No, okay. Let me go into closed strings now. Okay, so closed string. That is a typical drawing of a 4-point closed string amplitude. And now this has the topology of a sphere. And if you just believe me, what we said before about the insertions of the vertex operators and the fact that the conformal invariance allows you to just replace this states. This is states with an operator. By the way, I'm saying that you see this is a state. This is a quantum mechanical state with some momentum. So I'm mapping it to an operator. That's a pretty big statement. Okay, that you can map as a quantum mechanical state in a Hilbert space to an operator in a field theory. That's a pretty big statement, and this is true because this theory is conformal. And in conformal field theories, there's something called the state operator map. And only conformal field theory allows you to do this. And because the worship theory is a conformal field theory, this is why you can do this. So again, conformal field theory, it's crucial for all these things. So notice that this is tree level, and the previous thing was also tree level. If you wanted to compute a 1-loop level amplitude, then this would have to be something like that, like a little torus. A 2-loop, another hole. A 3-loop, another hole, things like that. The same thing as before. For example, here, if you wanted to compute an open string at 1 loop, this would be a hole. So that would get mapped to a disk with a hole, which is called an annulus. 2 loops, and this with 2 holes. And then you will have to integrate over all possible sizes of the holes and things like that. That's how it's people compute loop amplitudes in string theory. But let me stay at tree level, so there's no handles, there's no holes whatsoever. Nothing goes on inside, but by just the joining and splitting of these closed strings. So this so that's my little cartoon for a sphere. And notice that now again, because this is quantum mechanics, we have to integrate for all positions of these vertex operators. But before, for the case of open strings, those vertex operators were obligated to be just on the boundary of the disk. And now, in the case of the closed strings, this thing could be anywhere on the surface of the sphere. So you have to integrate over the sphere for each of the positions of these vertex operators. So you will have things like this. What one usually does is that you do the stereographic projection. So you project the sphere onto the complex plane with the one of the poles identified with the origin and the other one identified with infinity. And when you do that, you end up with an integral over 4 copies, in this case, of the complex plane of something here, something that depends on, again, on S and T, blah, blah, blah. And now you can ask the same question. Okay, so in the case of the open string, you had this remaining SL2R invariance. Would you have something similar in the case of the closed string? And the answer is yes. And if maybe you already guessed that now the only difference is that this gets upgraded into the SL2C group. So again, the SL2C, what it does is that with the same constraint, that's the S, TC equal to 1. So again, it allows you to fix 3 of the vertex operators. So you end up integrating only over 1. But now it's an integration over the entire complex plane. So our rule of thumb is that if you see a string amplitude and you see just one, you don't see a 2 here, it's because you're seeing an open string amplitude, and if you see that 2, it's because you're seeing a closed string. Okay, so it has some form like that. Okay, and in the case of for closed string tachyons, you get I'll give you the answer. You get again like a product of gamma functions like that, but it's no longer the Euler beta function, but it's very similar. Yeah, okay. Let me give you the answer for the superstructure.
Sure, that's correct.
Are
you sure?
What?
That's correct. What do you mean?
Right, in terms of S and T and masses.
What?
Let
Let me finish it up. I mean, you might be right, but I don't think. So, the nice thing, assuming I wrote it correctly, now it's correct? Okay, yes. Okay. In the case of the superstring, yeah, but can you erase that? Now I'm doing gravitons, okay? Because it's important in gravity school. I want to show it. I want to show the graviton. So closed strings. In this case, for the graviton case, remember in the closed string, in the closed string spectrum, again you have the symmetric part, the antisymmetric part, and the trace part. So you have gravitons, the Calderon and dilatons. If you focus on the graviton sector, this is what you get at tree level for the superstring. And you see that what I have written here is the tree level 3-level amplitude for 4 graviton scattering that you get in GR. Okay? So now as an exercise, expand this thing in powers of alpha prime. If you expand around alpha prime equals 0, okay? What you get is that this is equal to 1, okay? And then you get more corrections. Okay. So the very first term, because this becomes 1, gives you exactly the amplitude of gravitational physics. Okay. So this is why, and if you do that, here, you also get something similar. If you take the alpha prime going to 0, I wanted to show it, but yeah, time is I don't have much time. But if you did it here, you will get the amplitude for a lambda phi cube theory. Okay. If you want to know more details about it, you can ask me later. The mass of the tachyon gets promoted. Becomes the mass of that scalar field, and that was shown a long time ago at the very beginning of at the very early days of string theory. So if you did the same thing here, then the first thing that you get is the 4-point graviton amplitude in general relativity, and then if you compute corrections to it, if you leave the alpha prime corrections, you would get corrections to this graviton amplitude that you could. Then you can ask you can do reverse engineering and ask the same question. Okay, what is the Lagrangian that would give you that correction to for the graviton amplitude? And this will become alpha, what are called alpha prime corrections to general relativity. That's yeah. Okay.
So they give higher curvature terms in the Lagrangian, essentially.
Yes. Exactly. Okay, so I will finish with this. I will finish with the following thing. I have not said I haven't said anything about high energies. So here we go, and this is what I'm going to show you in the last 3 minutes. So no.
So okay, I'm trying to remember. So this amplitude is for the superstring for gravitons it's close the string, right? Is that
Yeah.
the way it had to be?
Yes.
So is the r squared to the 4th term included in this amplitude? Because it has a different tensor structure.
The
From
R4.
Yes. Because there is
You mean Ricci to the.
so if I compute,
But by R you mean Ricci or?
if I compute the amplitude of 4 gravitons in like 2 strings, I have the one that comes from Einstein-Hilbert, but I also have alpha prime cubed times something that comes from curvature squared.
Yeah.
Curvature 4. Is it there? I don't remember.
I'm sure. I mean, it should be there. I haven't checked it, but it should be there.
Was it so different
Because it's not-
structure?
Because I think the tensor structure is there.
You say that tensor structure is not here.
It's not here. Yes.
You could be right. Yeah. You might be right. But that would be. But again, that would correspond to high derivative terms, right?
That's right.
So in the strict.
Because I think that equal sign there, I don't think the first one, I don't think it's completely true. I think there is some approximation there. So I'm not sure, I'm trying to remember.
I mean, there could be something that
Yes.
is awarded alpha prime and some other tensor structure here. Is that what you mean?
Alpha cube.
Alpha cube, yeah.
Yes.
Yeah, but that will be subleading for small alpha prime.
Correct.
So at leading order alpha prime, is it still true that you get just pure gravity?
It's because if it's leading order of a prime, that most of those stuff they cancel. Right? I just get.
Yeah, you just get
Yeah.
1. Actually, get -1. I forget it's a minus. Yeah. No, yeah, I agree. Yeah, okay. I agree that I did not write it correctly. If I intended to write it for final alpha prime, and I forgot I forgot these things over here. I totally agree. I kind of cheated a little bit.
You compute the term them to get an expression for them, and then you expand them further.
Yes.
And you discover the first term is just
It's
general
GR.
relativity.
Yeah, I
You
did
don't
not-
have these gamma terms.
What?
If you are doing an approximation, you don't have that gammas control.
Exactly. If you expand this thing, I mean, these things become. You gotta get 1 plus st over the square. I forgot. S plus d square, things like that, times power of alpha prime and so on and so forth.
Yes, then the R to the fourth term is T8 with the polarizations and all.
Probably, yeah.
All that come from the same
Yeah, but the full one, the one that I did not write completely.
no 4.3 lambda.
Oh yes, it's no. I mean, like this, all that. Yeah.
It's isolating the term.
Are you claiming that the 4 point amplitude is just the first term?
No, I mean, that's what I wrote at the beginning, but as Breno pointed out, I was missing some terms
It's
here.
just isolating something.
Yeah, but isolated the thing that
It's
dominates
proportional to-
when alpha prime goes to 0. So I just wanted to show that in the limit when alpha prime goes to 0, you recover GR, which is still true,
Yes.
right? Because this is subleading. Right? But I know that I was a little bit messy in the sense that if to show that what is the full alpha prime dependence of the full amplitude, I should have written the thing here that I forgot. I totally agree. Okay, so yeah, I ran out of time. 5 more minutes? Okay, thanks. Okay, so what do we really mean by high energy in string theory? So in QFT, remember that S had dimensions of energy squared, right? So when you say high energy in any computation where you have massive particles in the spectrum, so high energy correspond to S much larger than your masses squared in the strings, we have a dimensional full parameter, which is alpha prime. The alpha prime is basically what's called the string length squared. So alpha prime has unit and string length squared. So if you remember, the amplitude that we had before, which was, for example, minus alpha prime s minus alpha prime t. Let me show the full thing for the random case. Okay. Notice that alpha prime comes multiplied with some momentum squared all the time in all this object here, right? So this is unitless. So that's dimensionless. So in every time you do, of course, an expansion, when you say something is big or something is small, you have to take the big thing or the small thing. It has to be a dimensionless number, right? This is what you should do. So this is what one means in string theory when you go to high energy. Okay. So alpha prime times the Mandelstam to be a number much larger than 1. Okay. So if you do that, now just as a homework exercise, do that for the case of the 4 graviton amplitude in the superstring. Let me just intentionally forget that I'm going to write it here in GR for graviton. Okay. Let me forget about let me just put ellipsis for the moment. but this is just for academic reasons. And so now take this limit. So take the limit when all these arguments go to infinity. So you can use the Stirling's approximation that you learned at the very beginning. And then you see that these things in that limit become something like this. Minus alpha prime times this, and something like that. Okay, I'm not going to show what the full dependence is, but that function is a function of the scattering angle only. So the only dependence in the energy of the scattering process is like this. Okay, and this is not how it appears, but this is just to emphasize the fact that this is a positive thing with a minus sign. So in the limit when this goes, it's very large, the amplitude is exponentially suppressed at very high energies. This is unlike any field theory that we do. Okay? In field theory, in QFT, in any QFT that you want, that satisfies all the requirements from unitarity and Lorentz invariance, locality, whatever. At high energies, it goes usually like this. This is called the Forsyth bound. Okay, so if the theory is unitary because of quantum mechanics, in QFT, they cannot grow with the energy faster than that form over there. Otherwise, if it's, for example, s to the cube, that theory is not unitary. Okay, so it's a sick theory. So all well-behaved QFTs, they have to satisfy this bound. But notice something, that for large energies, this thing grows. It's not allowed to grow, too fast, but it grows. In the string theory, it's completely the opposite. Not only satisfies that bound, but actually, it's exponentially suppressed at high energies.
It's a bound. Maybe you have some field theory that's way below the bound. It's just a bound.
Yeah, I agree. But again, in quantum field theory, there isn't such thing as an exponentially suppressed amplitude in the like, you're right. So yeah, maybe I should have said that in those words. That's the thing that's most important. Okay, so this kind of exponential suppression only happens in string theory, and at the end of the day, you can. This is actually one of the reasons why string theory is finite. It's a finite theory. That all loop corrections at the end of the day, you don't see UV divergences in loop amplitudes. So let me finish with this, and tomorrow at the beginning of the lecture, I'm going to show a very quick computation that does not involve string theory anywhere. Okay, I'm just going to show you a computation that people have done in the past. Beethoven, for example, and I was saying this yesterday, that if you have a scattering in which this impact parameter is of the order of the Planck length, okay, or smaller than that, then this is going to create a black hole. And then it's going to look like this. You have two particles scattered. There's some black hole production in between, and then this black hole decays into two particles again. Let me just focus on that process, for example. It could decay on many other particles, of course. Let me just focus on that particular computation. And what I'm going to show is that in the high energy regime, this thing also behaves something like this, some other function. Okay. So it's a pretty neat example in which, and this is what we were saying yesterday, in which, you can read it, in two different ways. You can say that the string theory knows about black hole creation, or if you're more conservative, you can say, this is just a string theory is a theory of quantum gravity, and this exponentially suppression is something universal to quantum gravity. Okay. Okay, so let me finish with that.